Hi all, welcome back to this video tutorial, and this video is for solving a university question asked for a previous year COA examination, and this question comes under 5th module topic, and the question is: design a 4-bit arithmetic unit which perform the following operation on two input A and B controlled by selection variables S1 and S0 and input carry Cin. And for this question it carries 10 marks. Okay, and this is the function table which is given for value S1 and S0. If both are 0, with Cin equal to 0 it perform operation addition, and with Cin equal to 1 the function out is A plus B plus 1, and with values 0 1 for selection variables, with Cin 0 it perform a transfer operation, and with Cin equal to 1 it perform A plus 1, an increment operation. With S1 equal to 1 and S0 equal to 0 it perform complement operation of second input B. That means transfer the complemented form of B input. And with Cin equal to 1 it perform complement plus 1 operation. That means perform a 2's complement conversion of second input. Okay, so with S1 equal to 1 and S0 equal to 1 the function output is A plus B complement, and with Cin equal to 1 F equal to A plus B complement plus 1. How to solve this question? For solving such question, any question like this, we can follow the same procedure that is going to discuss in this video. That is, here it is given as we have two selection lines, selection input S1 and S0 with two input A and B, and here we have a combination circuit that derives an output which forms the Xi and Yi input of the parallel adder, and this parallel adder carries a C input value and it generates a function out. Okay, so this our task is to find out the combinational circuit which form the output, the Xi input of this parallel adder, and this combinational circuit with these four input, it form a particular combination circuit which form the Yi input of this parallel adder, and for its working it also consider the Cin value. Okay, so our task is to consider or derive the various combinational circuit that form the Xi input as well as the Yi input. A separate combinational circuit form an Xi input, another circuit form the Yi input of this parallel adder. Okay, so what is the general working principles, what are the steps, or what is the procedure for finding such a combinational circuit here? So in order to derive such a combinational circuit, we need to analyze this function table which was given here, and we need to compare with this processor design principle and understand basic input combinations used in order to get these function output. So consider the case with S1 equal to 0 and S0 equal to 0. We want to get a function output as F equal to A plus B when Cin equal to 0, and it must generate a function output A plus B plus 1 with Cin equal to 1. So consider these two function values which must occur during S1 equal to 0 and S0 equal to 0. Okay, so what are the input combination we need to get such a function output here? With Cin equal to 0, we want to get A plus B as the function output. When Cin become 1, we want to get A plus B plus 1 as the function output. So analyze these diagrams. So here it is the A plus B output generating parallel adder. What is the input configuration here? Here we need to set A as the X input, B as the Y input. With Cin equal to 0, then it generates A plus B. Okay, so in order to get this one with Cin equal to 1, we need X input as A, Y input as B. So this one satisfied with this combination. Okay, this combination of output, function output, is possible with this particular input configuration. Set X input as A itself, set Y input as B itself. Okay, next condition, with S1 equal to 0 and S0 equal to 1, we want to get a transfer operation. Transfer A input itself when Cin equal to 0, and when Cin equal to 1, we want to perform an increment operation of A input. Okay, so this is the case. With Cin equal to 0, it perform transfer operation of X input of this parallel. Whatever value we are given to the X input of this parallel adder, it will transfer to the output part when Cin equal to 0. When Cin equal to 1, it will perform an increment operation of this X input of this parallel adder. So this is the case. What is the input configuration for these two combination? Here the input configuration is X input must be A itself and Y input must be full of zeros, right? So in order to get such a output combination with Cin equal to 0 and Cin equal to 1, what are the input configuration we needed? Here we need X input of this parallel adder as the A input itself and B with full of zeros. Okay, so consider next case. Here with S1 equal to 1 and S0 equal to 0, we want to get B complement as the output function and B complement plus 1 as the output function when Cin equal to 1. So this particular combination of output function, this particular combination is not directly available from this A diagram. It's not directly available. So we can make certain changes to this input configuration in order to get such an output function combination. When Cin equal to 0, we want to get B complement as the output function. With Cin equal to 1, we want to get B complement plus 1 as the output function. How it is possible? Just consider this one. Is there any similarity with this combination? Yes, here we have a similarity with this particular combination. In order to, with Cin equal to 0, we need a transfer operation. With Cin equal to 1, we need an increment operation, but the value we want to get incremented is the B complement. So make certain changes for this input configuration, that is make the X input of this parallel adder with full of zeros, right? With B input as, the Y input as B complement. Is it right? So consider once more, this is just a modification of our previous case, this one. With Cin equal to 0, we need to transfer one output. In order to transfer one output to the output function line, what we want to perform, set the data we want to transfer as the input of this parallel adder. Here we set the first input, that is the X input, as A and other as full of 0. So in order to transfer V complement to the output line, what we want to perform? We want to perform make the X input of this parallel adder with full of 0 and Y input as B complement, right? So in order to get this function f equal to B complement plus 1 when Cin equal to 1, what we want to do, or what changes we want to make here? In this diagram, we make the A input or the X input of this parallel adder with full of zeros and the Y input make it as B complement, right? So this changes to the input configuration derive this particular combination of output function with respect to Cn equal to 0 and Cn equal to 1. Right? Now this S1 equal to 1 and S0 equal to 0, with Cn equal to 0 we need f equal to a plus b complement as the output function, and with Cn equal to 1 we need f equal to a plus b complement plus 1 as the output function, which is directly available from this 8 function implementation. These two combination shows the S1, S0, 1, 1 cases. Right? What are the input combinations, or what are the input configuration required here? In order to get a plus b complement when Cn equal to 0, we need the x input of this parallel adder as a itself and the y input of this parallel adder as b complement. And here also with Cn equal to 1, set the x input as the a itself, y input as the b complement in order to get function output as a plus b complement plus 1. Okay. So now we need to derive this combinational circuit that form the xi input in general, and similarly derives another combinational circuit that form the yi input of the parallel adder in general. How to derive such combinational circuit? In order to derive that, consider the situation, consider the inputs S1, S0, AI, BI, and these two form the parallel adder xi and yi inputs. Okay, with S1 equal to 0 and S0 equal to 0, what's the input requirement? We get output as a plus b and a plus b plus 1. In order to get an output a plus b when Cn equal to 0 and a plus b plus 1 when Cn equal to 1, what are the input combinations? X input must be a itself, y input must be b itself. Here also x input must be a itself, y input must be b itself. That means whatever value we are going to give to the a input, it makes the x input directly. Whatever value we are going to give for the b input, it makes the y input of this parallel adder directly. So whatever value, what are the four possible combination for this AI and BI? They are 0, 0, 0, 1, 1, 0 and 1, 1. Whatever value given to AI, it will directly form the xi input. So here it is 0 for AI, so it directly form the xi input. 0 here. Again 0, here also 0. 1 for AI, it directly form the xi input, and this one for AI, it directly form the xi input. Similarly for BI and yi also, whatever value given to BI, it directly form the yi input. So 0, 0, 1, 1, 0, 0, 1, 1. Right? And the next case is S1 equal to 0 and S0 equal to 1. S1 equal to 0 and S0 equal to 1. And what we want to get, the output function is, when Cn equal to 0, we want to get a as the output function, and Cn equal to 1, we want to get a plus 1. This is the case. And for this particular combination, what is the input configuration? X is whatever value given to a, it directly form the AI input, and yi input always kept as 0. No need to consider the value given to BI. That means whatever value given to BI, the yi input always set as 0. So how can we set this output functions? With combination 0, 0, whatever value given to AI, it directly form the xi input. So 0, 0, 1, 1 directly form 0, 0, 1, 1 here. But for BI, whatever value given to BI, no need to consider the value of BI, put full of zeros here. Okay, because the second input, whatever value given to BI, no need to consider, the yi is always kept as 0. So put full of zeros here. Right? And next is 1, 0. S1 equal to 1 and S0 equal to 0. We want to get output function as b complement when Cn equal to 0 and b complement plus 1 when Cn equal to 1. This is just a modification of the previous case. So how to make this output function. Make the xi input or this a part full of zeros in both the cases, and make the yi input of this parallel adder as b complement. That means whatever value given to this yi complement, take the complement of that form and transfer to the output, and make the ai or the xi input of this parallel adder always kept as 0. That means here we have no a part in the or a value in the output function. That means a is always kept 0 here, right? And the b is obtained or represented here in its complemented form. So we need to implement or we need to input the complemented form of b as the yi input, just like as given in this particular diagram. In order to get a plus b complement, we want to apply the complement of b to the yi input. Similarly, in order to transfer this b complemented form to the output function, output line, we want to set this yi input of parallel adder as b complement, and here the a part is absent. That means kept the a input as full of zeros. So in case of 1 0, a is always 0. Whatever value given to a, no need to consider this. Just put full of 0 for the 4 combinations here, and whatever value given to b, we need to take the complement of that value and take assign it as the yi input. So for bi equal to 0, take the complement as the yi input. So put here 1. Okay, for bi value as 1, so take the complement and set as the yi input, that is 0 here. For 0, kept 1 as the yi input. For 1, kept 0 as the yi input. And the fourth and last case, that is s1 equal to 1 and s0 equal to 0, the expected outcome is a plus b complement, and with sin equal to 1, we want to get a plus b complement 1 plus 1 as the output function, a plus b complement plus 1 as the output function, right, which is directly available from this particular combination. What is the input configuration for this combination? In order to get such a output function with sin equal to 0 and sin equal to 1, make the xi input of this parallel adder as a itself, and make the yi input of this parallel adder as b complement. Complement of b is kept as the yi input of this parallel adder in both this case. Okay, so make this combination for 1 1. With all 4 possibilities of ai and bi, a is kept as a itself. So 0 0 1 1, here for xi also 0 0 1 1, and bi is kept yi is kept as the complemented form of bi. So for 0, here assigned the complement of bi, that is complement of 0 1 here, and for 1 value, with if bi equal to 1, assign its complement to the input of yi, that is kept 0 here. For 0, kept 1 here, 1 set 0 here. Okay, is it clear, this table? Now we want to make a simplification for this xi and yi in order to get the combinational circuit. Here we have 16 values, so here we mark the 16 values in the schema map, and we need a simplification. While simplifying, by combining these 4 ones together and these 4 ones together, we get an expression like this for this xi, that is s1 complement ai plus s0 ai. This forms the combinational circuit for this xi input of our parallel adder. And similarly, combine this 16 values of vi arranged properly in the schema map, and while simplifying this, we get a combinational circuit for this yi input of this parallel adder as s1 bi complement plus s1 complement s0 complement bi. Okay, now we can draw the circuit. Consider the question again. Here we want to design, for this question is for designing a 4-bit arithmetic unit. So we need to each parallel adder consider only a single bit manipulation. So we need 4 parallel ladder for completing the 4-bit arithmetic operation. Right? So this is the diagrammatic representation of our previous example. We need 4 parallel adder unit. Each one unit generate a single bit manipulation output. Okay, so S1 here, S1 complement, S0, S0 complement, and for Xi input we need S1 complement AI plus S0 AI. Okay, so draw this, combine these values properly. S1 complement A1 plus S0 A1. For the first parallel adder we have the input A1 and B1, and for the second parallel adder we have the input A2 and B2, and for the third parallel adder we have the input A3 and B3, and here A4 and B4 with the same selection lines S1 and S0, and an external Cin is connected with the first parallel adder unit. Its Cout is taken as the Cin of second unit, and so on, and finally the Cout of the last and the fourth parallel adder is taken as the final Cout value. Okay, so Xi is connected with a combinational circuit S1 bar A1 plus S0 A1, and Yi is connected with a combinational circuit S1 B1 bar plus S1 bar S0 bar B1. Similarly here for the second parallel adder circuit, the S1 bar A2 plus S0 A2 is connected with X2 input. The circuit S0 B2 bar plus S1 bar S0 bar B2. It's not a complement form here. S1 bar S0 bar B2 plus S0 B2 bar is connected with Y2. Similarly here S1 A3 plus S0 here we need S1 bar A3 plus S0 A3, which is connected with A3. S1 bar needed. Okay, S1 bar A3 plus S0 A3 is connected with X3, and S1 B3 bar plus S1 bar S0 bar B3 is connected to Y3. Here also S1 bar A4 plus S4 A4 is connected with X4 input of this parallel adder. S1 B4 bar plus S1 bar S0 bar B4 is connected with Y4 input of the last parallel adder. We have here it is a mistake, that is we need S1 bar here. Okay, not the change. Here we need S1 bar here because the first expression of this Xi, the general expression of this Xi input is S1 bar that means S1 complement AI plus S0 AI. So we need a bar here, S1 bar or S1 complement A3 plus S0 A3 connected to X3. S1 B3 complement S1 bar S0 B3 is connected with Y3 input of the third parallel adder. Similarly here also, here we need S1 complement A4 plus S0 A4 connected with the X4 input of this fourth parallel adder. S1 B4 complement plus S1 complement S0 complement B4 is connected with the Y4 input. Okay, so this is the answer, final answer for this particular question asked for the previous university exam. So if we know the procedure, we can derive the combinational circuits for any such questions, and we can score the full 10 marks. Okay, so find the expression properly and draw the diagram. Okay.